Hello, this is Eileen Solomon. We're going to be, in this video, talking about some techniques where Laplace transforms are used to solve initial value types of problems in differential equations. And we're going to look at an example of several of each of the types of problems that are on the Unit 3 review sheet at Trident Technical College for Laplace transforms. So the first objective is to review using the table of Laplace transforms to find the Laplace transform for different functions of t. And if you don't have your Laplace transform sheet handy, let me pull it up on this worksheet. So you probably were given by your instructor just a half a sheet that had these rules on them. So we can refer back to that table as we need to for the problems that we're going to be given. So let's start with example 1 and work the problem. Find the Laplace of a given function of t. So if we had, let's say we wanted the Laplace of e to the negative 3t minus 4 times sine 6t plus 3. Okay. All right. So according to our chart, we have a way of finding the Laplace of each one of these terms. And we can look at our green sheet or our table of Laplace transforms and refer to find out what each rule is. And we know the linearity quality of Laplace would allow us to go one term at a time and find the Laplace of each type of term. So for the first term, the Laplace of e to the negative 3t would satisfy rule number 2, e to the at. And the Laplace of e to the at is 1 over s minus a. So this first term would simply be 1 over s minus a negative 3, which would make it s plus 3. Notice that the rule says that the sign of the constant in that denominator expression is the opposite of the sign of the coefficient of t. All right, the next term is minus 4, and that needs to be multiplied times the Laplace of sine 6t. Well, rule number 3 tells me how to find the Laplace of sine bt. I do b over s squared plus b squared. So that would be 6 divided by s squared plus 6 squared, and 6 squared we'll go ahead and do and write that on 36. Let me minimize the Laplace table. And the Laplace of 3, that was just rule 1, is 3 times the Laplace of 1, which is 3 times 1 over s. So you can simplify that as much as you want to and get a sum of fractions, sum of difference of fractions. I would probably do the arithmetic and simplify the b squares and any products that you might have had, but I probably would not simplify to get a common denominator. I would leave it written as a sum. So that's all that's asking you to do, is find the Laplace of that expression. Okay? All right, let me move this thing down just a little bit, and let's go ahead and do another example. This one is one of mine. It is not on your review sheet, so I thought we'd work just a plain old piecewise function example. So we're going to assume that f of t is equal to 4 if t is between 0 and 5 for the first piece, and then 6 if t is between 5 and 8, and negative 2 if t is greater than 8. Now the first step in finding the Laplace of a piecewise function that does not have t's in the definition of each piece is to use the unit step function. So we're going to rewrite f of t as a sum of functions. So let me put it down here. F of t is equal to, right, so the first function value, if it's not 0, then that has to be a term by itself. So we'll have 4 plus. Now to find the next coefficient of the unit step function that takes over at t equals 5, I have to subtract my new function value at 6 minus where I was at 4, and that becomes the coefficient of u of t minus 5. The a value of 5 is where that jump occurred from the first definition to the second definition, t equal 5. And then plus the last piece, the coefficient, is -2 minus where we were, which was at 6, times u of t minus the a value where that change occurred, which was at t equal 8. So you're simply going to do that arithmetic and write this as 4 plus 2 times u of t minus 5 minus 8 times u of t minus 8. And now you can look back at your chart. The next to the last rule on your table of Laplace says that the Laplace of u of t minus a is e to the negative as over s. So the Laplace of the first term, that's using rule 1, is just 4 over s. The Laplace of the second term is 2 times the Laplace of u of t minus 5, which is e to the minus 5s over s. Now notice the coefficient of s in the exponent is the same sign as what we had in our t minus a expression. And then the last term minus 8 times e to the negative 8s over s. So that would be the Laplace of that particular function. Okay? All right, so there's 2 examples of finding the Laplace of a particular function of t. Let's go to an extension of the page. Let me erase these stray marks that I've done on the page. All right, now for the third example, I want us to do a piecewise function that does have t's in the definition. So this is f of t equal -1 if t is between 0 and 3, 2t minus 7 if t is between 3 and 5, and then 3 if t is greater than 5. Okay, so the first step would be to rewrite f of t in terms of the unit step function, kind of like we did on the previous problem, except we'll have t's in it this time. So since my first piece is not 0, I need a term with just the -1. And then plus. I'm going to start my grouping symbols around this. So where I am at 2t minus 7 minus where I was, minus a -1 is the same as plus 1, and that's going to be multiplied times the unit step function of t minus 3, because that's where that change in the function values occurred. Then the next piece and the last term would be the quantity 3, where I am at the last definition, minus both of those terms. 2t minus a -7 will give me a plus 7, and that's times u of t minus 5. And you want to simplify that. So you go ahead and do the arithmetic or the algebra of combining your like terms in each one of those coefficients. So this function becomes 2t minus 6 times u of t minus 3. And then this one is going to be 10 minus 2t, basically, times u of t minus 5. Okay. Now, if you look at the chart, the very last rule for the Laplace of a piecewise function that's got t's in it says that the Laplace of f of t minus a times mu of t minus a can be found. Well, that means I need to think of this function right here as a function of t minus 3. So I'm just going to call it that. I'm going to rename this. I'm going to say here's -1 plus some function that we don't know called f sub 1 of t minus a times u of t minus a, where the t minus a matches in both of them, which means these have to be identical, right? Those have to be the same. And then this has to be some function, let me call it f sub 2 of t minus 5 times u of t minus 5, which means these have to be the same. Once I have that, then the Laplace of f of t rule is given for each one of these terms that's given in the chart. Okay, the Laplace of the -1 would be -1 over s. And then according to rule number 12, the Laplace of f of t minus a times u of t minus a is e to the negative as, so e to the negative 3s, times cap f, and I'm going to label this cap f sub 1 of s, and we'll have to find that before we can finish this up. Plus, and now f sub 2 times f sub 2 of t minus 5 times u of t minus 5, same rule. It's going to be e to the negative 5s times cap f sub 2 of s. Okay, get rid of my string marks here. All right, so now the challenge is, how do I find cap f sub 1 and cap f sub 2 as functions of s? So I'm kind of going to do those separately. So let's go back to where we had our f sub 1 of t minus 3 introduced. We said f sub 1 of t minus 3 had to actually be equal to 2t minus 6, the multiplier in front of u of t minus 3. And I need to know what f sub 1 of t is. So all I do to get that is I replace t on both sides of the equation with t plus 3. And when you simplify that, 2t plus 6 minus 6 is just going to become 2t. So you knew the function of t minus 3 already, but what you need to know is the function of just t, because the Laplace of this is what we're calling cap f sub 1 of s. So the Laplace of 2t, according to rule number 5, is 2 times 1 over s squared, or 2 over s squared is all we're going to have for the Laplace of that. All right, and then we said f sub 2 of t, I'm going to do that one, f sub 2 of t minus 5 had to be equal to 10 minus 2t. So similarly, I've got to find the function of just t by replacing t on both sides with the quantity t plus 5. T plus 5 minus 5 is where the t came from on the left. And now when you simplify that, 10 minus 2t minus 10 is just negative 2t. And that means the Laplace of that function, we'll call cap f sub 2 of s, is negative 2 over s squared. Okay? So now back to the Laplace of the original function that was given to me. I went a little bit too far. Let me back up just a little bit. All right. So we were at the Laplace of f of t. Let me come back down here and let's continue with that. So the Laplace of f of t, according to what we've just done, is negative 1 over s that we already had from that first term, plus e to the negative 3s times cap f sub 1 of s, which was 2 over s squared, plus e to the negative 5s times cap f sub 2 of s, which was negative 2 over x squared. Now you can leave it like that as far as I'm concerned, or you can rewrite it negative 1 over s plus 2 e to the negative 3s over s squared, oops, gotta have the s, over s squared, and then minus 2 e to the negative 5s over s squared. That's a little bit prettier, and that's kind of traditional for the final answer on the Laplace transform of a function of t. Okay? So when you take the Laplace of any function of t, you should end up with, like we did on this third example, you should end up with just a function of s. So that's all there is to that type of problem. And I am sure that on your test, you would have a few problems that just had you find the Laplace of some given functions of t. All right, now I already did those examples, so let's skip these because I had already written them on the same slide. All right, so now the next objective is that we find the inverse Laplace of each function of s. All right, so I've picked a few of these examples for us to do, and let me double check to see that I haven't already got it typed. Well, there we go. That was the one I was going to do. So given in example 4, cap f of s is equal to the fraction 4 over s plus 3 plus the fraction quantity 5s plus 6 over the quantity s squared plus 3, we want to find the inverse Laplace of this by finding rules that match each piece. Now the first fraction really could be rewritten as a product of the constant 4 times 1 over s plus 3, and that's the way I want to think of it. And then the second fraction, I'm going to separate. So I'm going to write 5s over s squared plus 3 as 5 times s over s squared plus 3 plus 6 times 1 over s squared plus 3. So remember, when you have more than one term in the numerator divided by a denominator, you can separate the fractions by separating the numerator terms over the same denominator. And that's all I've done here. 5s over s squared plus 3 plus 6 over s squared plus 3. Now, thinking about going backwards, you want to find rules that match the last column of your Laplace table, which, let me pop that back up for just a minute so you can see it. All right, so in the last column here, we have these particular functions of s. And the first rule, 1 over s plus 3, looks like it matches rule number 2. And so the inverse Laplace of what we have, and I'm going to click back on the original notebook here. So the inverse Laplace, which we could call inverse Laplace of kappa of s, would be 4 times the inverse Laplace of 1 over s plus 3. And that's e to the negative 3t. Remember here, the coefficient of t in this rule is the opposite sign as your constant in the denominator. Okay? If you look back at your chart for the s over s squared plus b squared, that involves rule 4, a cosine. So if we take out the 5, the coefficient, then the inverse Laplace of s over s squared plus b squared is cosine of bt. Now in this case, b is whatever is squared to give us 3. So that means b is the square root of 3. So this is the square root of 3 times t. The square root does not include the t. Okay? Now to make the last fraction inverse Laplace to find it, I need to make that fraction look exactly like rule 3. And rule 3 required that I have b over s squared plus b squared. So that means I need to multiply and divide by that missing b constant to get the b value that we didn't have up there. Okay? All right, so now that is equivalent, and I could write plus 6 over the square root of 3 plus 6 square root of 3 over 3, just multiplying by square root of 3 over the square root of 3, times the sign of bt. And then you can simplify that fraction. 6 over 3 is going to make that a 2. So we end up with 4 e to the negative 3t plus 5 cosine square root of 3 times t plus 2 square root of 3 times sine of square root of 3 times t. Okay. And that's the inverse Laplace of the original given function of s that we had. If you're looking at your review sheet, that was actually problem number 7 on the review sheet. Right? Example 5. Right, so this time, example 5 is going to be a matter of rewriting. Yeah, we have one fraction to find the inverse Laplace of, and the denominator is not matching any of our current rules. We don't have an s squared plus b squared the way it's written right now. If we had a factorable denominator, then we would do a partial fraction decomposition. But on this problem, s squared plus 4s plus 6 does not factor. So we have no choice but to use completing the square. All right, so let me just keep the numerator the way it is. Now let's just work on the denominator rewrite, okay? So s squared plus 4s, I'm going to pull that part out separately, plus 6. Same exact fraction, just written, grouped a little differently. So to complete the square on s inside the parentheses, I would need to add half of b squared. Half of 4 is 2. 2 squared is 4. And I can't add 4 without subtracting 4, so the plus 4 minus 4 has to be there. And now if I rewrite that in its factor form, now I have s plus 3 over s plus 2 quantity square plus 2. Now we are close to matching one of our rules. In rule number 9, you'll notice we have a denominator of s plus a quantity square plus b square. And in rule 10, we have a denominator of s plus a quantity square plus b square. So the key here is, because I need a s plus a on top, or just a constant b on top, I still have to rewrite the numerator now. So I'm going to still work on the rewrite. Okay, we're going to go one more step. I'm going to take the s plus 2 over the denominator that I need and separate out the extra plus 1 over the same denominator. So now the first fraction looks just like rule 10, s plus a over s plus a quantity square plus b square. The second fraction, unfortunately, doesn't have the b that we need in the numerator to make it match rule number 9. No problem. All we're missing is the square root of 2. So multiply and divide by the square root of 2 to get it. Okay? So now our rules match, and the inverse Laplace can be done using those two rules. All right, so for the s plus a over s plus a squared plus b squared, that's rule 10. And the inverse Laplace of that is e to the negative 2t times cosine of bt, where the b is the square root of 2. So that's my angle. The next term had a 1 over the square root of 2. If you rationalize that, that is exactly the same as square root of 2 over 2. And then the inverse Laplace of square root of 2 over s plus a squared plus b squared is rule number 9, which says e to the negative 2t times the sine of square root of 2 times t. And I don't know why I wrote the sign so far down. It's supposed to be on the same line. Okay, so that is the inverse Laplace of that single fraction that we were given. So one important reminder is, whenever you have a quadratic denominator in a proper fraction, that is bottom heavy degree, if it's not factorable, then you're going to need to use completing the square to rewrite it. And then once you get it rewritten using completing the square, you'll know what you need as far as the s's in the numerator. You'll need the s plus a if you've got any s's at all, instead of just s. Okay. Example 6. Now you'll notice a little bit different scenario, because we have a product of a function of s, and that's the fraction, times e to the negative pi s. So to be able to find the inverse Laplace of cap f of s, we are probably going to need to use the very last rule, rule number 12. And on that particular problem, let me write down the rule just so you'll have it here. It says that the Laplace of f of t minus a times u of t minus a is equal to e to the negative as times cap f of s. Where cap f of s, remember, stands for this is the Laplace of your function of t. All right, now remember, we're trying to go backwards. So what we have here is a function of s right here. I'm going to call that cap f sub 1 of s times e to the negative pi s. And according to the rule, using the rule backwards, the inverse Laplace of this, of that function of s, the original cap f of s function, is going to be equal to little f sub 1, because we subscripted this thing, this little f sub 1 of t minus a. Well, what's the a? The a comes from the coefficient of s in the exponential. So the a is going to be a, t minus a. In this case, ours is t minus pi. Okay, so t minus pi times u of t minus pi. All right, so that's what we're trying to find. We're trying to find what is this f sub 1 of t minus pi. All right, so now you're going to concentrate on simplifying cap f sub 1 of s and rewriting it so that you can find the inverse Laplace of it. So you don't use the exponential in this part because remember cap f sub 1 of s here just stood for whatever the exponential was multiplied times. So what we're going to do is separate the two fractions. You know, you've got two terms in the numerator. So you're going to write a 4 times s over s squared plus 5 minus 5 times 1 over s squared plus 5. And you're going to use your inverse Laplace rules to find little f sub 1 of t. Now that notation stands for the inverse Laplace of cap f sub 1 of s. All right, so this is using the rules. So the s over s squared plus b squared rule is cosine. So I'm going to get 4 times the cosine of square root of 5 times t minus, now this one's missing a b in the numerator. So all I'm going to do is multiply by b and divide by b to get it. And 5 divided by the square root of 5 is the square root of 5. So if I rationalize, I can simplify that fraction to just be square root of 5. And then the inverse Laplace of square root of 5 over s squared plus 5, that's the b over s squared plus b squared. So this would simply be the sine of the same angle, bt. Okay? Now what we needed, remember, from here is f sub 1 of t minus pi. So to find that, all you're going to do is substitute and replace t with t minus pi. So you're going to get 4 times the cosine of square root of 5 times t minus pi minus the square root of 5 sine of square root of 5 times t minus pi. Okay. Now, I would just leave it written as a piecewise function. If I were working this problem, I wouldn't want to leave it with a unit step function in. Sometimes our textbook does. So if you think, put this back here where we had the f sub 1 of t minus pi, and that is the multiplier on the unit step function. So our final inverse Laplace, if you will, which ordinarily we would call just f of t with no subscripts because the original function was cap f of s. So the inverse Laplace would be f of t. I'm going to write it as a piecewise function. And the unit step function, remember, has 0 for all the values of t between 0 and wherever that a was. And in this case, the a value was pi. And then it has the function value in front of the unit step function for all the other t's. And in our case, it's all the stuff that we just had for cosine of square root of 5 times t minus pi minus square root of 5 times the sine of square root of 5 times t minus pi. And that's for all the t's that are greater than pi. Now, technically, the definition of the unit step function included the 0 and didn't include the pi until the second piece. So technically, that's what you should write, but most teachers don't care if you use open inequalities instead of closed inequalities for your piecewise function definition. But this is the answer to that problem. That is the inverse Laplace of our given function of x. And there's no trig identities that would really help us with simplifying the cosine of square root of 5 times the quantity t minus 5. If it had just been the cosine of t minus pi, we could have used the difference identities to simplify both of those terms, but because of the square root of 5, yeah, this time we can't. Okay, so I would assume that there would be several problems like these where you'd have given functions of s, and you would be asked to go backwards to find the inverse Laplace of those functions of x as functions of t. Right, so let's continue. The third type of problem would be applying the Laplace to solve initial value problems. Right, and I've picked a fairly simple example of this that does not have a piecewise function in it to start, and it's written here as example 7. So our differential equation is y double prime minus 6y prime minus 7y equals 0, which would be a really easy one to solve using techniques we already know. But remember, the advantage of Laplace is you've got the initial conditions over there on the right, so you can substitute the initial conditions at the very beginning of the problem. So the technique for solving initial value problems using Laplace is to start out by taking the Laplace of every term on both sides of the differential equation. In the case of a y double prime, the rule for finding the Laplace of y double prime is to take s squared times the Laplace of little y, which I'm going to call cap y, minus s times y of 0, which was given to be 7, minus y prime of 0, which was given to be 9. Okay, so all of that is the Laplace of y double prime. And then we have the middle term, minus 6 times, and now I need the Laplace of y prime. Well, the rule for the Laplace of y prime would be s times Laplace of y minus y of 0, which was given to be 7. And then the Laplace of negative 7y is minus 7 times Laplace of y. Fortunately, the Laplace of 0 is 0, so we don't have an ugly mess on the right-hand side. Okay, so it's very important that you review the rules for finding the Laplace of y prime and the Laplace of y double prime. Next step is to collect like terms on the left. So we're going to start by collecting all of our cap y terms. So from the first quantity, we have s squared times cap y. From the middle one, we have minus 6s times cap y. And from the last term on the left, we have minus 7, all multiplied times cap y. And then you're just going to get your other terms together. So simplifying, we get minus 7s minus 9 plus 6 times 7 is 42 equals 0. Okay. Do this arithmetic to combine these constants. That's the same as plus 33, negative 7s plus 33. And your next step is to move any terms that don't have cap y in them to the opposite side of the equation. So I'm going to leave this the way that it is. And I'm going to add 7s, and I'm going to subtract 33. You get an equivalent equation. And the last thing you want to do is divide both sides by the coefficient of y. Now, as I do that, I'm going to see that this is factorable, and so it will be helpful to go ahead and factor that denominator as s minus 7 times the quantity s plus 1. Anytime you have a quadratic denominator that is factorable, partial fraction decomposition is next. So our goal is to rewrite cap y as the sum of nice simple fractions. I want something over s minus 7 plus something over s plus 1. Now to find out what, let me just set it up here to be a over s minus 7 plus some constant b over s plus 1. Remember, when I have linear factors in the denominator, I just need a numerator that is a constant. If I multiply both sides of this equation by the original denominator, the product of s minus 7 times s plus 1, make sure you check your factoring, by the way. All right, we would get the numerator 7s minus 33 equal a times s plus 1 plus b times s minus 7. And then if we pick two convenient substitutions, for example, if I let s be negative 1, then the a would drop out because -1 plus 1 is 0. I might have an equation that just has b in it. So -7 minus 33 is -40. And then 0 plus b times -8. Dividing both sides by -8 gives b equal +5. And then another good substitution would be to let s equal 7. 7 times 7 is 49. 49 minus 33 is 16. And I'd have a times 8 plus b times 0, so b is gone. And we get quickly a equal 2. So now we know to use y equal 2 over s minus 7 plus 5 over s plus 1. If your instructor allows you to use technology and you have a TI-89 calculator, then your alternative to doing all this partial fraction decomposition work would be to use expand on your TI-89. Expanding the original fraction would give you this decomposition. But remember, on the final exam, no calculator, so you need to make sure that you know how to do these partial fraction decompositions analytically without a calculator if it comes down to that. All right, now to finish and solve the differential equation for the original variable, now you're going to use inverse Laplace. So I'll distinguish this with a cursive little y. So this is my function of t that I'm trying to find. So according to my chart, each one of these fits rule number 2. 1 over s minus a. So this is going to be a 2 times e to the positive 7t. Remember, the coefficients have to be opposites in this rule. Plus 5 times e to the negative 1t. So it saves me, by using Laplace, it saves me from having to go back and find the derivatives and use the initial conditions on the general solution. I'll have to find the general solution first and then plug in my initial conditions to get an equation that has a C1 and a C2. And then I'll have to do the derivative again and plug in the y prime information. Much, much faster if you're good at partial fraction decompositions. That's really the key to being able to work those problems. And of course, you might have an initial value problem that has piecewise functions in it, which just means it's a little bit more work, but the same basic techniques would apply to what we've done in the past. Okay? All right, so I'm going to do this in steps. And step 1 is going to be find the Laplace of the right side. All right, to do that, I'm just going to call the right-hand function h of t. I'm going to let h of t equal the piecewise function on the right. And to do this, I'm going to have to rewrite it with the unit step function. So it'll be t plus the quantity pi minus t times u of t minus pi. Okay. Now, the first term, we know how to find the Laplace of it. Cap h of s, the Laplace of this, according to the rule, would be 1 over s squared plus. Now, remember that this has to be some function of t minus pi right here. So let's call this, I will use f, let's call this h sub 1, little h sub 1 of t minus pi. If that's what this is, according to the last rule on my chart, the Laplace of a function of t minus a times u of t minus a is e to the negative as, which is e to the negative pi s, times cap f of s. In this case, it would be cap h sub 1 of s. Okay? So now all I have to do is find cap h sub 1, and I'm all set. So kind of pull out the little h sub 1 of t minus pi. What was it equal to? Well, it had to be the same as the coefficient we had down below it, in pi minus t. So clearly, those are just negatives of each other. If I replace t minus pi with t, I'm just going to get negative t. That's sloppy. Let me fix that. Negative t is what I'm trying to write. Or I could replace t with t plus pi on both sides, and that would make the pi's drop out and just leave me negative t. And we need cap h sub 1 of s. So that stands for the Laplace of that, and the Laplace of negative t was negative 1 over s squared. So now let's come back and let's finish this. This is 1 over s squared plus e to the negative pi s times negative 1 over s squared. Okay. So that's the first step. The first step is to find the Laplace of the right-hand side function of s. If it's a piecewise function, that requires rewriting it in terms of the unit step function, which is why I called it h of t. I didn't want to get it confused with the y's that were going on. And then I needed to find the Laplace of that, and to do that, I took the Laplace of each term using the appropriate rule. Laplace of t matched rule 5. Laplace of some function of t times u of t minus 5 has to be done with rule number 12. So I had to find out what my cap h sub 1 of s was, and that's what we were doing all this work for. All right, let me scroll down further, and let's do step 2. All right, so now step 2 is going to be to find the Laplace of both sides. Now we already know what the Laplace of the right is, so we can just plug that in. But the Laplace of the left side is going to require our derivative terms. So let me copy it again. We have y double prime plus 4y equal what we basically called h of t. And our initial conditions were that little y of 0, excuse me, y, yeah, that was supposed to be y of 0. Let me fix that. Little y of 0. I use a lowercase y in my writing, so I use that here too. Was given to be 2, and y prime of 0 was given to be 3. All right, so taking the Laplace of both sides will involve using the initial conditions when I do the Laplace of derivatives. So the first term is going to be s squared times Laplace of little y minus s times y of 0 minus y prime of 0. Now all of that is the Laplace of y double prime, plus 4 times the Laplace of little y, which is called 4 cap y, equals all that stuff we just got for the Laplace of h of t, okay, which we said was the Laplace of h of t, was this cap h of s, 1 over s squared plus e to the negative pi s times, actually, why don't we rewrite that as a difference so we don't have to keep writing plus. Right, so minus e to the negative pi s over s squared, or times 1 over s squared. Okay. All right, so now that we've done the Laplace, now I want to solve. All right, so at this point you want to isolate cap y. So we will get our cap y terms together, s squared plus 4 times cap y times cap y. And then we want to move these other terms to the right-hand side. So I'm going to have to add 2s, I'm going to have to add 3, and then I already have these other terms, so they'll still be there. And now the last step in isolating cap y is to divide everything by s squared plus 4. Okay, so cap y equal 2s plus 3 over s squared plus 4 plus 1 over s squared times s squared plus 4 minus the exponential e to the negative pi s times 1 over s squared times s squared plus 4. So basically you just get this extra factor of s squared plus 4 in each denominator. All right, now the easiest way to finish this thing is to do 2 partial fraction decompositions. Rewrite these 2 inside the brackets, rewrite that with 1 big partial fraction decomposition. You should do that because you'll have some like terms if you only use partial fractions on the second fraction. You'll have some like terms that will combine with the ones that you have right here. So if you have technology, just do one big expand and rewrite everything inside the brackets in simplified form. And then you want to do the same thing with this quantity, do a partial fraction decomposition on just it. All right, so I use technology just to speed up our work on that part of it. I mean, it's not difficult to do the partial fractions, but it is time consuming. So when you rewrite, the left-hand side now becomes 2 times s over s squared plus 4 plus 11/4 times 1 over s squared plus 4 plus 1/4 times 1 over s squared. And, well, there we had a minus because we changed it, so let me get rid of that plus, minus the exponential times, and then when I did the partial fraction decomposition on the second one, I got 1/4 times 1 over s squared plus 4 minus 1/4 times 1 over s squared. Okay? So at that point, we've simplified, we've rewritten, but we don't completely have things that match our rules just yet. So the key issue would be the b over s squared plus b squared, that we're missing the b on this particular fraction. So I need to multiply and divide by 2 to get the b value in the numerator. Same idea right here. I'm going to need a 2. So multiply and divide by 2. So this is now cap y equal 2 times s over s squared plus 4 plus 11/8 times 2 over s squared plus 4 plus 1/4 times 1 over s squared, leaving it that way because it makes it easier to use the rule. And then minus the exponential times, and I'm going to think of all of this stuff right here as, let's call it cap f of s. Some cap f of s. Now, according to the chart, to find little y, all I have to do is use the inverse Laplace. Remember, cap y stood for the Laplace of little y. Little y is a function of t. Cap y is a function of s. So little y is going to be 2 times the cosine of bs, which is 2t, not 2s. It's a function of t, plus 11/8 times the sine of 2t, plus 1/4 times t, or we could call it just t over 4. Let me rewrite it that way. 1/4 times t is the same as t over 4. And then the Laplace using the very last rule, inverse Laplace of an exponential times a function of s, is going to be little f of t minus pi times u of t minus pi. Very similar to how we did the inverse Laplace earlier. Okay? All right, now we still have a little bit more work to do because remember, we can't leave any answers with u in them. We've got to rewrite them as piecewise function. So let's just pull the cap f of s down for a minute, and let's rewrite cap f of s. So cap f of s was 1/8 times 2 over s squared plus 4 minus 1/4 times 1 over s squared. So we need to know what the inverse of that is, because that would be our function of t. So the inverse Laplace of this is 1/8 times the sine of bt, 2t, minus 1/4 times t, which is minus t over 4. Well, here I go again. That's hardly readable. Let me fix that. So minus t divided by 4. So I want to find f of t minus pi, which means I replace t with t minus pi. Well, 2 times the quantity t minus pi is going to give me 2t minus 2 pi. And from your knowledge of trig, I hope you remember that subtracting or adding 2 pi or integer multiples of 2 pi gives me the same thing as not subtracting the 2 pi. So basically, that's going to drop out and just leave me sine 2t times 1/8. So if I come back up here and I plug that in, now I've got little y equal 2 cosine 2t plus 11/8 times sine 2t plus t over 4 minus, this whole thing is subtracted. And it's multiplied times u of t minus pi. Okay? So the last step is to write it as a piecewise function because I've got a unit step function in there. So little y, there's only one part of it that has the u, so there's only going to be 2 parts. The first function value is the part that doesn't have u in it. So 2 cosine 2t, all these terms at the beginning, plus 11/8 sine 2t plus t over 4. And that's going to be for all the t's from 0 to pi. It's kind of traditional to use the same inequality intervals that you had in the original differential equation problem. So it was strictly between 0 and pi, so I left it that way. Now to find the second piece, we have to do all of this plus, or in this case, minus the change. So we have 2 cosine 2t, that's not going anywhere, that's still going to be there. And then we have plus 11/8 sine 2t, but we're going to subtract 1/8 sine 2t. Well, that's going to give us 10/8, which is the same as 5/4 sine 2t. And then we had a plus t over 4 here, minus a negative t over 4, which is going to be plus another t over 4. So we're going to get 2t over 4, or t over 2. And that's for all the t's that are greater than pi. Right, now let's look back and make sure that we've done that right. So we had our 1/8 sine 2t minus t over 4. And then we had to subtract both of those terms. So it was the same as adding t over 4 and subtracting 1/8 sine 2t. So this is how we want the final answer to be written in terms of the piecewise function, not in terms of, I might have reduced that fraction wrong. Yep, no, I think that's correct. We had 11/8 minus 1/8. Yeah, that's correct. So 11/8 minus 1/8 is 10/8. 10/8 is 5/4. So that is correct. Okay. All right. Now I did not bring an example of a system of differential equations solved with Laplace because that problem takes a little bit longer. If we need to, I'll do a separate video for how to use Laplace to solve a system of differential equations. That's probably the last thing you did in this unit, so you may remember how to do that. It's basically do the same thing, take the Laplace of both sides of both equations, collect your cap x terms, collect your cap y terms, and then use regular algebra elimination methods to eliminate cap x, and then solve for the remaining variable little y using inverse Laplace. And then go back and reverse those. Kill cap y, solve for the x. Okay? So I wish you luck on this unit. I hope you'll find Laplace transforms are helpful.